Hey everyone, my name is William Wu. I am a sophomore from Rancho Cucamonga High School. Today I'll be presenting my project on the simulation of H self-similar fractional Gaussian processes. Simulations of these processes could be used in finance, or financial analysis could use these to predict stock trends and risk management, and they could also be used in a variety of other fields. First, for some background on the topic, self-similarity is the property that part of an object is similar to the whole. The image of the mountain on the left displays features of self-similarity. In fact, it was actually generated by a computer using this property, as shown by the picture below it. A famous example of self-similarity would be the Weierstrass function, which when zoomed in looks like the whole. The mathematical notation of self-similarity in probability theory is given by equation 1. Here's an overview of stochastic processes. Stochastic processes are non-deterministic probability models, meaning the process is random. H self-similar fractional Gaussian processes, which is the main focus of this project, exhibits self-similarity, which is determined by its index h, more on that later, with multivariate normal distribution or bell curve distribution involved. A popular example is fractional Brownian motion. Its applications include hydrology, biology, and finance. The fractional Brownian motion is defined through its covariance function, which means how related two parts of the process are. Examples of fractional Brownian motion are shown on the right with different h values. So, for problems and goals. So, for the problems, in literature, there currently does not exist a unified, general way to simulate all H self-similar fractional Gaussian processes. And there exist case-by-case studies that detail the simulation methods for certain processes such as the fractional Brownian motion or Gaussian white noise. Concurrent methods rely on niche properties such as stationarity or having an integral representation to simulate the processes. For example, Wood and Chan's method. And the goals are to develop a unique and novel simulation method for all H self-similar fractional Gaussian processes through the use of the Lamprey transformation, generalize our method to simulate multifractional Brownian motion, and use our method to simulate sample paths of fractional Brownian motion and multifractional Brownian motion, and compare the results to existing simulation methods. A little on the Lamprey transformations. The concept of the Lamprey transform was introduced by John W. Lamprey in 1962. Given a stationary process U, the Lamprey transformation of U is defined in equation 2. Conversely, the inverse Lamprey transformation is defined in equation 3. The key thing to know about the Lamprey transformations is that they transform stationary processes into self-similar processes and vice versa. Stationary processes have the property that the distribution remains the same regardless of time, which is a very elegant property that will be used later on. Here is the simulation algorithm, which is the main contribution. In order to simulate a self-similar process V, we need to simulate the discrete sample path of V1 over n to V of 1. The main reason why we simulate the discrete sample path is summarized by the picture below, in which we simulate a bunch of points to form a continuous path. The algorithm is given below. To simulate the stationary sample path in step 1, we employ Wood and Chan's 1994 algorithm for simulating stationary Gaussian processes. Here's an example with technical details simulating fractional Brownian motion. Our simulation algorithm requires the explicit covariance function for Wood and Chan's method to be employed, which we calculate below for fractional Brownian motion. We also have an error control, which the approximated output and the real output have a mean squared error that approaches 0 at O of epsilon n plus log n over n. The result is statistically acceptable. So here are our simulation results for fractional Brownian motion. 1,024 points of fractional Brownian motion were simulated using our algorithm, which is pictured below. And it can be noted that simulating a self-similar process in the interval t within 0 to 1 is enough to produce the entire path due to the property of self-similarity. So the figure on the left is h equals to 0.2, while the figure on the right is h equals to 0.8. And it's also noted that when h is a small number, the path is more rough, and when h is a higher number, the path is more smooth. Here are the results for multifractional Brownian motion. It was introduced by Peltier and Levy-VL and is defined via the covariance function. MBM is locally asymptotically self-similar. We could decompose MBM into two independent processes, which we simulate the first using existing literature, while we simulate the rest using our method. And the graph of MBM that we simulated is depicted in the image with the Hurst function 0.6t plus 0.2. Quick look at the comparisons between our method and Wood and Chan's method. It can be seen that our method beats Wood and Chan's method in both fractional Brownian motion and multifractional Brownian motion. Conclusion: we suggested a novel and efficient way to simulate self-similar processes. Our method also fills gaps in simulating some classes of self-similar processes, and simulation of self-similar processes can be applied to various different fields. For the future, our idea could be applied to simulate self-similar random fields. Thank you for watching.